Hi Year 10. This first video is designed to talk you through the first learning intention for this final topic in Physics Year 10, which is magnetism and electromagnetism. So let's have a look through the PowerPoint, which is the one that I've posted in the newsfeed onto your LMS. Use your A3 sheet and annotate that as we go through so that you're making meaning of the diagrams. I've pasted those in and printed them for you, so you don't need to draw them all out, but it would be useful for you to use this as we go. There we go. I don't know why that's animated. Okay, so let's go through the learning intentions here. You need to be able to identify ferromagnetic materials, and we've done an investigation on that one. Accurately draw magnetic field patterns, indicate the direction a compass will point in a magnetic field, draw the Earth's magnetic field, describe how to make or to destroy a magnet, and what is meant by the terms hard and soft iron core. So I will just explain the idea of the lodestone. So natural magnets are found in terms of when magnets were first discovered. It was identified that lodestone, which is magnetite, actually has a magnetic field around it, and certain materials respond to it. Let's just have a look at what is magnetism itself. So a magnet, oh, these animations. There, let's start with this one. A magnet is usually iron, and it has a magnetic field around it, and different materials called ferromagnetic materials will respond to that magnet or be attracted to it. Here are some diagrams of magnets. And firstly, a horseshoe magnet, as you can see here, and then the bar magnet. So these are the two that we've used in class. So what does magnetism actually mean? It means that it exerts a force on particular types of materials. And how does it do that? So magnets and ferromagnetic materials have domains inside, so collections of billions of atoms that respond to a magnetic field. In permanent magnets, such as the ones that you've used in the classroom, those domains are aligned with a north pole and a south pole. And that gives the magnet a north and a south end. Okay, so what you know from playing with these magnets is that north is attracted to south, and you can feel when you pull those together, you can feel the magnetic force. But when you align two north poles together, you feel that repulsion. Okay, so that's one of the basic principles of magnetism, is that opposites attract. Not dissimilar to the electrostatic attraction we were doing in chemistry. Okay, so the positive and negatives attract. Here we have north and pole. North pole and south pole attract to each other on a magnet. You've tested a range of ferromagnetic materials, and hopefully what you've recorded is that iron, cobalt and nickel were the ones that responded to the permanent magnet that you used in your experiment, and other metals or materials didn't respond. Some alloys, such as stainless steel, it will depend on the proportion of different metals or different elements included in that alloy. So an alloy being a combination or a mixture of different things. It will depend on the exact percentage of the metals included in that alloy as to whether it is ferromagnetic or not. So the paper clips, even the ones we tried the other day, some of the paper clips respond very well to a permanent magnet and others don't. Okay. Now, permanent magnets always have a magnetic field around them. We also, when we played with the paper clips, we also were able to identify the fact that once one paper clip attracted to the magnet, that paper clip itself became magnetic. So what we were looking at there was something called magnetic induction. Let me see if I can find the image that I'm talking about. So Come on, leave that. There. So this here is an example of magnetic induction. So a paperclip, as you know, isn't a permanent magnet itself, but when you attach that to a magnet, it was then able to collect other paperclips in a long chain. So what you've been able to do is use a magnetic field to align the domains inside the paperclip and cause those to have a north and a south pole. And that in response can then collect or attract the next paperclip in line. Okay, let's just have a look here. The other thing we've looked at in class is the Earth. So we know that we say about the Earth, we say that we have a North Pole on the Earth, and that's often it's seen as in the top of the Earth, towards Europe, and we're down towards what we call the geographic South Pole of the Earth, down towards the bottom of the Earth, often when you see it in a diagram. It's really important for you to note and remember that we've named these places geographically as the geographic North Pole and the geographic South Pole. But in actual fact, what that means is the geographic North Pole attracts the North Pole of a magnet, of a compass. So on your compass, the little arrow here is actually a mini magnet itself, and the North Pole of that mini magnet is being attracted to the geographic North. What that tells you is that the geographic North can't be the magnetic North, because otherwise it would repel this North Pole of the mini magnet there. So geographic North of the Earth is actually magnetic South, or thereabouts. So that's just an important thing for you to keep in mind. Why is it so? It's because the core, the metal core of the Earth that we're standing on actually gives the Earth that magnetic field. Okay, so that's why we can use a compass with a tiny thin magnet inside of it to do our navigation when we're in cadets, because it will point to what we call geographic North, and that will remain unchanging throughout your expedition. But worth keeping in mind that what we call geographic North is actually the magnetic South, and what we call geographic South, or the South Pole, is actually magnetic North. Okay, let's have a look at one of the first skills that you'll need. So the first thing that we've done practically is to use iron filings to scatter over the top of bar magnets and horseshoe magnets, and then draw magnetic fields. Let's have a look at this one here as an example. So, animations. This represents your bar magnet, and remember that the bar magnets do have a north and a south on. The horseshoe didn't always have that, but you can use the bar magnet's north to determine which is north on the horseshoe magnet to see if your bar magnet's being attracted or repelled. So on your bar magnet, when you drew the arrangement of the iron filings, what we needed you to draw was a continuous line going in a north to south direction. It must be a smooth line, and it needs to have arrows on that line showing the direction of the field. So a magnetic field has a direction, and it's really important for you to show that. The direction always goes from the north to the south, whether that's a bar magnet, whether it's on the Earth, whether it's on a horseshoe magnet. And the lines are annotated with little arrows showing that north to south direction. The lines must be smooth, never cross over, and be much closer together wherever that magnetic field is stronger. So here, as you get closer to the magnet, the permanent magnet, the lines are much closer together, and as you get further away, that magnetic field becomes weaker and the lines are further apart. So for you to be able to draw that without any of the lines crossing over each other is a really important skill for you to demonstrate in any assessment, and also on the practicals that we've done. There are two more things that you need to know about magnets and magnetism as part of this first learning intention. One of them is about breaking magnets. So let's see if we can find the slide. Here we are. So just have a look at this one. There. So it's important to know that we call a magnet a dipole. Di meaning two, poles, pole meaning poles. Okay, so it's got different ends, one being north, one being south. If you break a magnet in half, what you end up with is two smaller magnets, each with a north and a south pole. Okay, so you end up with two dipole magnets, not a monopole. You don't end up with a north magnet and a south magnet. So therefore you can't destroy a magnet by breaking it. If you break those two again, you end up with 4 mini magnets, and that keeps going and going and going. Okay, so it's a good idea to think of a magnet as having an end that is more north because of those little domains inside aligned in a north-south direction, and the other end is more south. So the domains inside that are also aligned in a north-south direction, okay, creating this north-south. And physically snapping it will not destroy the magnet and the magnetism, just create more magnets. The way that you can, however, destroy a magnet is by force. So hitting extremely hard is one way. So write that one down. Also by putting it in a constantly changing magnetic field. So by spinning the domains around and around and around and around, you can reduce or take away the magnetism in what would normally be a permanent magnet. And the third way that you can destroy a permanent magnet is by heating it. So there's a little YouTube here that I will post for you. Just talks about, if you just Google destroy a magnet, there's about a 3-minute video telling you exactly how to do that. And heat is one thing that's really important to magnetism. By increasing the heat, you can actually cause those domains to become misaligned. So they're not all pointing in a north-south direction, and therefore you can actually reduce the magnetism and take that away. So they're the 3 ways that you can change a permanent magnet from being magnetic to not magnetic anymore. Okay. And the final part of the learning intention, which leads nicely into the next part of our learning about electromagnets, is all about, let me just find the learning intentions for you. There we go. Is the idea that we can have iron with either a hard iron core or a soft iron core. Okay, so what that means is that some ions are permanently magnetic. So that the domains are fixed in place. Because of the structure within that metal, the domains aren't free to move around. Okay, so it's very difficult to reduce or increase the magnetism within a hard iron. But in a soft iron, we can actually turn on or off the magnetism there. So you will notice that sometimes an iron nail, if you hold it aligned or next to a permanent magnet, that iron nail will suddenly become a magnet and be able to attract paper clips. But if you remove that, then the iron is no longer magnetic and it won't any longer pick up paper clips. So that's an example of a soft iron core, and we'll be using that when we build an electromagnet, which is part of the next learning intention. Okay, so if you need to watch the video again, press stop, rewind and play. Ensure that you understand all of these learning intentions listed here, and then you'll be ready to move on. Well done.